In part 2, let's take a look at how to formally test for a correlation. So there's 5 steps in testing for a correlation. The first step is to state the null and alternate hypotheses. The second step is to test the assumptions of the correlation. Step 3 is to calculate the test statistic. Step 4, evaluate that statistic. And then step 5, interpret the results. So these are the steps we'll walk through and explaining this in the lecture. Then in the classwork portion, I'll show you how to write this out in the paper and go through the process, paste the relevant information, and interpret that correctly. And then for the homework you'll do that on your own. So first step is to state the null and alternate hypotheses. Remember HO stands for the null hypothesis. H1 stands for the alternate hypothesis or the research hypothesis. Sometimes you'll see an HA for alternate, and they basically mean the same thing as far as we're concerned. Then you have the colon, and then we have rho equals 0.0. So it's pronounced rho. It's a Greek letter. It kind of looks like a P. So rho equals 0.0. So the null hypothesis is that the correlation is 0, that there's no relationship between the two variables. The alternate hypothesis is that rho, again, rho is the correlation coefficient, that it is not 0. So it could be as low as -1, as high as +1. But what we're saying here is that it is not 0. It doesn't state the direction of the correlation, just that it's not 0. There is some correlation or some relationship. The next step is to test the assumptions. Different statistical tests, of course, have different assumptions. A lot of them are the same, but there's some variety that must be met before they can be used. And if the assumptions are not met, then it's possible that the results could be misleading. We might have a situation where there appears to be a correlation when in fact there really isn't, or vice versa. So the main assumptions, the 3 main assumptions associated with a correlation test or normality, that is that the observations for each of the variables are normally distributed. Homogeneity of variance. This means that the values of one variable are spread out approximately the same amount along all possible values of the other variable. And I'll show you a picture of what that looks like. And then finally, absence of outliers, both univariate and bivariate outliers. We've talked about univariate outliers. I don't believe we've talked about bivariate outliers. And all of these assumptions can be tested informally through a visual inspection of a histogram, so one for each variable, and a scatter plot. So of course, there's more informal ways and more formal ways to do this, and we'll look at the more informal ways this time around so you can get the idea. But of course, all the techniques we learned before about testing these assumptions, for example, creating standardized values, would of course apply here as well. So step 3 is to calculate the test statistic. So we would use SPSS software to generate the technical output. That's going to give us the statistics of interest. And step 4, we're going to evaluate that statistic. So it's going to give us a correlation coefficient, and that gives us the strength and direction. So strength, that's the higher, the closer to absolute value of 1, the greater the strength. And the direction of the correlation would be whether it's positive or negative. So it'll either have a positive or negative coefficient. And we'll also have a p-statistic, which tells us the likelihood that this observed relationship occurred by chance. Or in other words, how likely is it that we would generate this correlation coefficient if in fact the null hypothesis were true, that there's really no relationship in the population. The way we report them is according to this convention. So we have R in italics, and then in parentheses is the degrees of freedom, which is n-1, space equals space, 0.74, that's the correlation coefficient rounded to the hundredths place, comma, space, P in italics, space, less than space, and then whatever the next highest cutoff point is. So example 0.01. And so again, you would either have 0.05, 0.01, or 0.001 for our class. That's as far as SPSS will report. So it's the next highest conventional cutoff point. So this is the degrees of freedom, like I said a second ago, n-1, or 2 less than the sample size. So if I were to show you this output or these results and say how large is the sample size, you should know that it was 20, because n-1, so n-2, so 20 minus 2 is 18. Finally, interpreting the result. After interpreting the mathematical meaning, you might like to speculate about why these variables are related, what are the implications of this relationship. So this is where it's not just a math class. Always think about it in terms of what the variables are, what's relevant about this. One more piece of information you can get from these statistics right here is if you square the correlation coefficient, so that is this term right here, the 0.74. So if you square it, 0.74 times 0.74, that's going to give you something called the coefficient of determination. And it's usually referred to or denoted as r squared because it is r squared. And this gives you the proportion of the variance of one variable that is predicted or accounted for by the other variable. Another way of saying that would be it's the shared variance between the two variables. And an r squared value can range from 0 to 1. 0 to 1. So there will be no negative r squareds because anything times itself, or any number squared, will be positive. And it wouldn't make sense that you'd have negative 10% of the variance shared. Right? So the higher the value, the more variance explained. So the example that we're going to do in the classwork is height and self-esteem. And so the data file is available on Blackboard. And there's two variables, height, so it's a continuous variable measured in inches, and then self-esteem, which would be a composite score on a standardized test of self-esteem, and that'll be treated also as a continuous variable. So the researcher has a theory that height increases individual self-esteem, so we're going to expect to find a positive correlation between these variables, although we'll still run a two-tailed test to be conservative. And we'll use the 5 steps outlined above to conduct a formal correlation test to test this hypothesis. So we'll pick this up in a different video, and that'll walk you through how to set up the Word file, how to run the test, and how to report everything.